In this highlight video, we're going to learn how to distinguish different chiral centers using what's called the RS nomenclature. Every chiral center has two possibilities. After watching this video, you will know how to classify those two possibilities as either being R or being S. Here's how we do it. First off, we need to identify whether the molecule has any stereogenetic centers. If it doesn't, then we don't have to do this. We then rank the different groups or the different substituents around the stereogenic center as ranking as 1, 2, 3, and 4. The ranking system focuses primarily on atomic number, with higher atomic numbers ranking higher. If we have to rank two atoms that are isotopes of one another, the higher mass will rank higher. If we have two atoms that are the same, so there's a tie, we move to the next atom until we find a difference. If we have multiple bonds, double bonds or triple bonds, we treat the multiply bonded atom as having an equivalent number of singly bonded atoms, and I'll show you how we do that in a minute. We then position the molecule by rotating it around to point the lowest priority away from us. We draw a circle from priority 1 to 2 to 3 and back to 1, and if that circle rotates clockwise, we call the chiral center R. If that circle rotates counterclockwise, we call it S. So let's try it on these two molecules shown at the bottom. Is there a stereogenic center? Yes, there's one right here because it has an OH, it has an H, it has a methyl, and it has an ethyl. So we need to rank the four different groups attached to that carbon. So we rank it based upon atomic number. Oxygen has a higher atomic number than carbon or hydrogen, so it's ranked number 1. The other easy one to do would be the hydrogen is going to be ranked number 4 because it has the lowest atomic number. We then compare the other two atoms. We have a carbon here and a carbon here, so we have a tie. So we then look at what's attached to those two carbons. This carbon on the left has 3 hydrogens attached to it. So we can write this out as 3H, H, H. The carbon on the right has a carbon and 2 hydrogens attached to it. Carbon, hydrogen, hydrogen. We always list them with the highest atomic number first. We then compare, starting on the left, we have an H here, we have a carbon here, and so this side ranks higher. Right? So this is going to be number 2, this is 3, and the H is 4. All right, we've done our ranking. Position number 4 away. Number 4 is on a dashed bond, and so it's already pointing away. We draw a circle from 1 to 2, from 2 to 3, and from 3 back to 1. Notice that our arrows are going clockwise. All right, so just like if you were turning the steering wheel of your car clockwise, which direction would it turn? It would turn right, and so this is an R stereogenic center. Let's try the one on the left. On the right, the one on the right is the enantiomer of the structure on the left. So let's do our ranking. Again, the OH is 1, the H is 4, The ethyl group is 2. The methyl group is 3. We draw our lines from 1 to 2, 2 to 3, 3 back to 1. We now have a rotation that is counterclockwise, and this is referred to as S. So R and S. When we have enantiomers, each enantiomer will have exactly opposite chiral centers. Let's try some examples. The molecule on the left, does it have any stereogenic centers? All right, is there one here? No, right? Because that does not have 4 different groups because we see 2 methyl groups attached. But this one right here is a stereogenic center. Like we've done before, it's best to add in any missing hydrogens. So we have a hydrogen going back, and now we can rank the substituents. OH again is number 1 because we go 1 atom at a time. Notice that there's a bromine on this substituent, but that bromine is far away. So we need to make sure to go 1 atom at a time. So we pick the oxygen is 1, the H is number 4, we have a carbon here and a carbon here, so these are a tie. So we look at what's attached. This carbon has another carbon out here and 2 hydrogens attached. This one over here has 2 carbons and 1 hydrogen attached. All right, now we compare. We start at the left because we put the highest atomic number atoms to the left. Carbon compared to carbon, still a tie. We go to the next one, carbon versus hydrogen, so this has a higher ranking. So this is going to be ranked number 2. This is number 3, even though it has a bromine, but we never made it out to the bromine. Draw our arrows. Number 4 is back, 1 to 2, 2 to 3, 3 back to 1, counterclockwise. What does that mean it is? It is S. All right, what about the one on the right? Is there a stereogenic center? Yes, right where the chlorine is attached. We add our missing hydrogen, and let's rank the atoms. Chlorine has the highest atomic number, so it's 1. Again, in this case, we have a hydrogen, which is number 4. And then we have to rank these 2 carbons. Right? This carbon, we know how to do it. It has a carbon here, a carbon here, and a carbon here. So it has only 3 carbons attached to it. When we list this, we don't list the stereogenic center. We don't go backwards. We only go away from the stereogenic center. So what do we do with this double bond? So remember, when I listed the rules, I said when we have a multiply bonded atom, we treat it as having an equivalent number of singly bonded atoms. So what that means is if I redraw this, okay, that this has an H. Let's fill in these atoms too. This has an H there and an H here. But this carbon right here had a double bond to this carbon, so we treat it like it's bonded to 2 carbons. Likewise, the carbon down here had a double bond back to the other carbon, so we treat it as being bonded to 2 carbons. All right, so we add these 2 carbons in, and then we do our classification. What's attached to here? Remember, we don't go backwards. This is connected to a carbon, carbon, and a hydrogen. All right, we compare these two. Carbon here first, carbon here, it's a tie. Carbon, carbon, it's a tie. But then we have hydrogen versus carbon. And so this position is going to be ranked 2. The double bond is going to be ranked 3. We have number 4. Look at that. Oops, number 4 is in front. So now we have to reposition the molecule. I'm going to rotate it, flip it over, so that number 4 is in the back. So I'm going to flip it so the double bond is over here. Just going to kind of rotate it around like this. The double bond's here. The 2 methyl groups are here. And because we flipped it over, the chlorine is now on top, and the H is in the back. Let's put our rankings again. 1, 2, 3, 4. We draw our arrows. 1, 2, 3, 3 back to 1. Counterclockwise. This is another S chiral center. The procedure we've talked about already will work every time, but let me show you a couple of shortcuts. Let's do the problem on the left. Right? Do we have a stereogenic center? Yes, right here. So what group is going to be number 1? All right, so we have a carbon, we have a carbon, we have a carbon and an oxygen. Oxygen has a higher atomic number, so this is number 1. All right, then we go to the next atom. All are carbons, so they're all tied. So then we look at what's attached to them. This carbon has a chlorine and an oxygen and an oxygen, because remember, we treat that double bond to the oxygen as being bonded to 2 oxygens. This one over here has fluorine, fluorine, fluorine. And what would we classify this as? Well, there's no hydrogens on there. This will just be carbon, carbon, carbon. Then we compare. Okay, chlorine, fluorine, carbon. All right, chlorine has the highest atomic number, so remember we need to remember our periodic table. So this is 2. Fluorine is higher than carbon, so this is 3, and this is 4. Notice that number 4, this benzene ring, is in front. Okay, so our rule says we need to rotate this molecule to put number 4 as pointing away. So we either need to orient number 4 away. Okay, this is the way that what the rules say. But because there really are only 2 possibilities, R or S, what we can do is go ahead and look at the rotation. Okay, we're going to follow the rotation, and then we are going to reverse our answer, right? Because there's only 2 possibilities. So we're going to go from 1 to 2, 2 to 3, 3 back to 1. This is going clockwise, which would give us R, but we're going to say no, it's not R, it's going to be S, but we have to say because number 4 in front. All right, so this is our shortcut. If the number 4, the lowest priority substituent, is pointing towards us, we can go ahead and do the rotation and simply reverse the answer. But if we do that on an exam, for example, we need to explain what we're doing. All right, one more example, one more shortcut. This is the last one we'll do. So let's look at the stereogenic center. Okay, we have 1. Let's rank the different groups. OH is number 1. What's going to be number 2? Okay, this is going to be 2 because that carbon is bonded to 2 carbons. This is 3. This is 4. So notice, I guess, as we did on the last one, number 4 doesn't have to be a hydrogen. It can be any atoms. It's just the lowest ranking group. Notice in this example, number 4 is not pointing away or forward, but it's in the plane of the drawing. So the shortcut we can do for this case, right, is that we can either follow the rule. We either orient number 4 away, and then we just follow the rules. Or our shortcut is to switch number 4 to the back. What that means is we'll take number 4 and whatever substituent is pointing away, it's the OH in this case, and we're going to switch these two groups. We're going to redraw it now. And our OH will be here. Our ethyl group still is here. And we switched the methyl group to the back. So now these are ranked 1, 2, 3, 4. Okay, we look at the rotation. And so that's going to be 1 to 2, 2 to 3, 3 back to 1. This is counter clockwise, which should be S, but it's not going to be S, it's going to be R, and we have to say because we switched two groups. All right, so in these examples we've seen how we can classify stereogenic centers as either R or S.